The purpose of this lesson is to investigate the fetch-execute cycle. You should be able to describe the stages of the fetch-execute cycle, and you should be able to describe and use register transfer notation to describe that particular cycle. In addition to that, you need to be able to understand the purpose of interrupts and understand how factors contribute to the performance of a computer system, what makes it go fast or what can act as a bottleneck. Now, again, there should be a bit of background from IGCSE with the fetch-execute cycle. You should know a lot about the basics, but we will also review those in this lesson. So let's start by a little true or false game, just to check your knowledge. On screen, you see a number of statements. You need to identify which one of these are true and which ones are false. So do pause the video and do have a quick jot down, and we'll go through these in a moment. Okay, so hopefully you've got the statements written down, which ones are true and false. So let's start with the first one. Virtual memory is cloud storage. This is false because virtual memory is nothing to do with cloud storage. It's more to do with using a backing store to complement your primary memory. We're going to be talking a lot more about that. Another statement, primary is equal to internal and secondary is equal to external. The first part of the statement is true. Primary is normally internal memory. Secondary obviously can be external, but it can also be internal. Cache equal to registers, that is false. Primary is equal to volatile, not really, because read-only memory is non-volatile, so that's quite clearly incorrect, so that's false. RAM always increases performance, that's false as well, because often other factors come into play. Secondary storage is used when RAM is full, again, that is incorrect as well, because that can lead to crashes unless you've got virtual memory being utilized. A 3 GHz performs better than a 2 GHz system. Again, technically it might be possible, but not really in real life, because RAM and other components can also play a significant part. So if you've got a faster processor but limited amount of RAM, that can act as a bottleneck as well. So hopefully you got those correct. Now we're going to look at key terms, and as usual, do pause the video and jot these down. You should know about the fetch execute cycle from IGCSE, which is a cycle in which instructions and data are fetched from memory and decoded and executed. You then have the different parts, program counter, what it does, current instruction register. Register transfer notation is new. It's basically a shorthand notation to show movement of data and instructions in a processor, and it can be used to represent the operation of the fetch execute cycle. So it's a quick way of representing that particular diagram that we all well and know. Interrupts are quite common from IGCSE, signals sent from a device or software to a processor requesting its attention. Interrupt priorities and interrupt service routines will probably be new. All interrupts need to be prioritized because you don't want the processor to be interrupted. And think about it this way, if 2 interrupts come in, which one do you deal with first? So there has to be a particular type of priority given to certain interrupts. So that's quite useful. The interrupt service routine or the interrupt handler is basically software which handles these requests, such as printer out of paper, and it will probably send the request to the CPU for processing. So this piece of software routine allows us to prioritize the different interrupts and lets the operating system come into play. Okay, hopefully you got these down. Let's get on with the lesson. Let's start with the story of the Traitorous 8. And just like von Neumann and Einstein and Oppenheimer and all of those greats from the era in the 40s where they did wonderful work, the Traitorous 8 have had a profound impact on the development of computers and computer science since the 60s. The story, though, originates back in the 1950s and starts with Stanford University, and a visiting professor there called William Shockley recruited a group of young PhD graduates, and his goal was to develop and produce new semiconductor devices. So he formed Shockley Semiconductor Lab, and William Shockley had already received a Nobel Prize in physics and was an experienced researcher and teacher, but he wasn't the very best of people to work for. He was very strict, very unpopular, very authoritarian, and these 8 people who were working for him eventually decided to leave and form their own company called Fairchild Semiconductors. And the 8 who left Shockley were Julius Blank, Victor Grinch, John Horney, Eugene Kleene, Jay Last, Robert Noyce, Sheldon Roberts, and someone called Gordon Moore. And these 8 were described as traitors, and Shockley felt their leaving was a betrayal, so the name Traitorous 8 came about because of that. Now, this newly formed Fairchild Semiconductor eventually grew up to become the leader of the semiconductor industry, and in 1960 it became an incubator for Silicon Valley. And poor old Shockley Semiconductors, eventually it lost business and became the site of a supermarket, and the only thing that's remaining of Shockley is just that sign that you see on screen. Fairchild Semiconductors has a significant legacy on the world, and we'll talk a bit more about that later. But also at the same time, what was happening was there was a massive heartbreak in the United States because the Soviet had fired the first Earth satellite into space, and there was a bit of a space war happening, and USA was coming second. So they wanted to launch a person into space and eventually put a man on the moon. And to do that, they required significant computing power. They needed semiconductors that could operate hundreds of thousands of times per second, and there was nothing like that in the world at that moment. And this is where Fairchild Semiconductors comes in, and one particular person, the person's name was Gordon Moore. Now, Kennedy at the time had made a vow to put a man on the moon, or American on the moon, by the end of the decade. This is in the 60s, so there was a lot of money floating around, but there was not a lot of development on the semiconductor front. And Gordon Moore was the one that published this influential article in a journal called The Electronics, where he talked about the doubling of computational power every 18 months to 2 years. So how do we go about cramming more components onto integrated circuits? And this was so inspirational at that particular point in time that it eventually led to the development of the 100,000 transistors on a chip for the fuselage to land the rockets on the moon. Now, Gordon Moore and Moore's law is so influential, and if you don't know who he is, he's the founder of Intel, and his Moore's law is still something that we adhere to today, and we keep on developing computers and we keep on reducing the size of microprocessors just to meet his predictions, or the doubling of computational power every 18 months to 2 years. And this article was published in 1965, so you can see that we've been doing it for over 50 years. So quite an influential man, and you can see the impact is still being felt today. So the end result of all of this was that in 1969, the Apollo 11 landed on the moon, and human beings for the first time stepped on its surface. So one small step for man has become world famous, and most people around the world know its significance. Now, the companies that came after Fairchild Semiconductor, or out of Fairchild Semiconductor, for example, Gordon Moore went on to found Intel, and the others went on to form companies like NVIDIA and AMD, and chances are that you're probably using some of their products right now. These companies have had a substantial impact on the world and how processors are being designed, whether they're used for general purpose or specialist or for graphics in gaming. These companies are at the forefront of that. Now it's becoming more and more difficult to sustain Gordon Moore's doubling of transistors on a computer chip every 18 months or 2 years. So a lot of different types of techniques are being used, and one of the techniques being used in the early days was overclocking. So the clock itself defines the clock cycle, which synchronizes all computer operations. The control bus transmits timing signals, ensuring everything is fully synchronized. So if you increase the clock speed, the processing speed of the computer is also increased. So an example would be that if you got a 3.5 gigahertz processor, that basically means it's 3.5 billion clock cycles per second. So you can alter and tweak it to go up to 3
3.6 or 3.8 or maybe even 4, but obviously there's a risk involved. Can you think of what the risks will be? That if you increase the clock speed to have faster computers, what could go wrong? So just think about that before we start discussing these answers. Hopefully you picked up the generation of heat, and also perhaps more errors could occur if you push the processor way past its design limit. Now, 4 factors need to be considered whilst looking at a system, and obviously we start with the width of the address bus in the data bus, because if it's a 32-bit address bus, you might have a 3.5 gigahertz processor. It's not going to be operating very fast compared to a 3.5 gigahertz system working with a 128-bit address bus. And similarly, overclocking plays a part. The clock speed can be changed by accessing the BIOS, and you can alter the settings. You probably can try that on your computer if you want to risk it. However, using a clock speed higher than the computer can lead to problems such as execution of instructions outside design limits, which can lead to unsynchronized operations. In other words, an instruction is unable to complete in time before the next one is due to be executed, and the computer will frequently crash or become unstable. And obviously there are serious overheating of CPUs, and you've probably seen those videos about using liquid nitrogen or helium to cool CPUs down. Then you can obviously use cache memory, which also improves processor performance, and there's different levels of cache. Now, cache is similar to RAM, that its contents are lost whenever power is turned off. Now, cache uses SRAM, whereas most computers use DRAM for the main memory. So it's speedier, and there are different levels that you can probably see on the top right hand corner. So the closer you are to the CPU, the more expensive cache gets, and the least amount of quantity that you actually have. So if you've got gigabytes, then you might have megabytes, and then you might go into kilobytes when you go down close to the CPU. Now, cache memories will have faster access times, since there is no need to keep refreshing, which slows down access time in general. When a processor reads memory, it first checks out the cache, and then it moves to the main memory if the required data is not available in the cache itself. Cache memory stores frequently used instructions and data that needs to be accessed faster, and this improves processor performance instead of going to the slower DRAM-based main memory. And finally, the use of different number of cores is another technique used to improve computer performance. Many computers are now dual core or quad core or octa core. Now, dual core basically means your CPU is made out of 2 cores which talk to each other. Quad core means CPU is made out of 4 cores and they can be linked to each other. So the idea of using more cores alleviates the need to continually increase clock speeds. However, the problem with that is that the doubling the number of cores does not necessarily double the computer's performance, since we have to take into account the need for the CPU to be able to communicate with each core, and this reduces overall performance. For example, if you look on screen, dual core has 1 channel and needs the CPU to communicate with both cores, reducing some of the potential increase. Quad core has 6 channels and needs the CPU to communicate with all 4 cores, considerably reducing potential performance. And think about how many you might need to have octa-core, where 8 cores need to talk to each other. Now, to summarize, the following factors impact a computer system's performance. Increasing the bus width, both the data and address buses, that increases the performance and speed of a computer system. Increasing the clock speed usually increases the speed of a computer. Computer's performance can be changed by altering bus width, clock speed, and the use of multi-core CPUs. And finally, the use of cache memories can also speed up a processor's performance as well. So, simply, more cache, faster computers, increased bus width, faster computers, more number of cores, faster computers, and increasing the clock speed by overclocking, faster computers. But if you increase the clock speed but have a reduced bus width, you're not going to see that much gain. And if you don't have enough cache memory, you're not going to see much gain. So it has to be a combination of all 4, and you've got to strike a balance to ensure that your computer is operating at the best possible speed. Now let's move on to the fetch execute cycle. To execute a set of instructions, the processor first fetches data and instructions from memory and stores them in suitable registers. Both the address bus and the data bus are used in this particular process. Once this is done, each instruction needs to be decoded before being executed. So the fetch stage, the next instruction is fetched from the memory address currently stored in the program counter and is then stored in the current instruction register. The PC is then incremented so that the next instruction can be processed. Then you do decode. This is decoded whatever is in the current instruction register so that each instruction can be interpreted in the next part of the cycle, and then it's executed. So the processor passes the decoded instruction as a set of control signals to the appropriate components within the computer system. This allows each instruction to be carried out in its logical sequence. So computers are basically sequential machines, and they process these sequential instructions so quickly that they give us the impression that they can handle multiple tasks simultaneously. Let's go into a bit more detail on to the fetch execute cycle. So first, this is something new for AS level, the register transfer notation. So the box on the bottom left hand corner, if you look on the right hand side, you will see the flowchart of the fetch execute cycle, and you can see how we can write that flowchart in a simpler notation. MAR is assign the value of whatever the data is in the program counter, and you define it by simply writing MAR, an arrow just like you would assign a variable, and the program counter, the data in the program counter, you need to put square brackets to denote whatever the data is. Now the next line says the program counter is assigned the value of the program counter plus 1. So if the current instruction in the program counter was 1, plus 1 means it will now go to 2. MDR is assigned the value of the data stored at the address shown in the MAR. For that you will need two brackets. So you're trying to get the data which is stored at the address which is shown in the MAR, and that data is copied into the MDR rather than the address at the MAR. If you just wanted to transfer just the address stored in MAR, then we just need to use a single pair of square brackets, but since we want the data that is stored at that address, then you use a double square bracket set. Now the register transfer notation is pretty simple, so hopefully pause the video and just get familiar with that. You also need to know about the use of interrupts in the fetch execute cycle as well. Like the CPU is dealing with the current instruction and something important comes and interrupts it. How would it handle it? A special register called the interrupt register is used in this particular process. So while the CPU is in the middle of carrying out its fetch execute cycle, and an interrupt occurs which will cause one of the bits in the interrupt register to change its status. For example, the initial stages might be 000, 0000, and a fault might occur while writing data to the hard drive. This would cause the register to change to 0000, 1000, and these are designed by the architect of the CPU to identify what the interrupt codes are. So just have a look at the fetch, execute and interrupt stages of the cycle. So pause the video and get familiar with it. Okay, so you will need to define this particular process in perhaps an exam question. So at the next fetch execute cycle, the interrupt register is checked bit by bit. Contents, let's just say 00001000 would indicate an interrupt has occurred during the previous cycle and it still needs servicing. The CPU would now service this interrupt or ignore it depending on its priority. Once the interrupt is serviced by the CPU, it stops its current task and stores the content of the registers. Control is now transferred to the interrupt handler or the ISR routine, and once the interrupt is fully serviced, the register is reset and the contents of the registers are restored. So when the process starts, the CPU is fetching the instructions, it's decoding the instruction and checks for the end of the program. If there is the end of the program, then it ends. If not, then it checks for any interrupts. Once it's checking for interrupts, if there are no interrupts, then it disables the interrupt because it's going to go back into the next instruction and it doesn't want anybody to interfere with it. However, if there are interrupts, then it moves on to the interrupt stage of the cycle. And in this particular stage, the interrupts are enabled and the interrupt priority is checked. So it suspends the execution of the current program and executes whatever's in the interrupt service routine. Now, based on the priority, it either deals with the interrupt or it goes back to its current instruction and it follows the flowchart all over again. And that's the basic process of dealing with an interrupt in the case of a CPU. Normally, it's dealt at the end of an instructions cycle, checks the interrupt register, and if there's something there, it deals with it. Otherwise, it just disabled interruptions and it continues on with what it's doing until the next instruction is resolved. So what exactly is an interrupt? An interrupt is a signal sent from a device or from a computer to the processor. Now this will cause the processor to temporarily stop what it's doing and service the interrupt. And it can be caused by a timing signal, input-output processes, hardware faults, user interactions, and software errors. Lots of different ways interrupts can be generated. The computer needs to identify the interrupt type and also establish the level of priority that a particular interrupt might have. So interrupts allow computers to carry out many tasks or to have several windows open, for example, at the same time. Whenever an interrupt is serviced, the status of the current task being run is saved. The contents of the program counter and other registers are also saved. The ISR is executed next, and it does that by loading the start address of the ISR into the program counter, and then it deals with the interrupt. It's fully serviced, and once the interrupt is dealt with, then and only then is the status of the previously interrupted task reinstated. So the contents of the saved registers are retrieved, and it continues from the point prior to the interrupt being sent. Now, by now, you should know what interrupts are and how a CPU handles interrupts. You should be able to explain the fetch, decode, execute cycle, and you should also be able to explain the different factors that influence a computer's performance. Do go over the video again if there's something that you're not sure of, and feel free to send questions my way. That's all for today. I will see you in the next session.